Hello viewers, welcome to Physics with Sanmitra. I am Sanmitra Phomik, and in this series of lectures of interference or wave optics chapter, today's topic is thin film interference. First of all, let me explain what is the film. Film is anything which is having a very thin layer. So now you can ask what is thin film. I would say the word this thin film, this is a bit redundant word because film itself signifies something very thin. So this thickness is very small compared to its length. This thickness is very small compared to its length. Then this sort of thing is called film. Now what forms a film? Suppose I am spreading oil on a surface. This is my surface and I am spreading oil on a surface. Now since I am spreading oil on a surface, now what I see here, that suppose I am incidenting a light here and this is coming like this. A part of the light is being reflected and this part is being reflected. Now if these two superimpose by some means, then we can find some fringe pattern or some interference pattern. So this is the origin reflected light and this light, these two can form fringe pattern. So exactly that is what I am going to show you today. That is the interference from thin film. So let me show you mathematically how it happens. I have told you the physically how it may happen, but mathematically let me show you. This is the light which is incident here, and see, when a ray of light is incident on a surface of the film, and the refractive index of the film is say mu, say at an angle I, and this refraction angle, a part of it is refracted and a part of it is, let me show with red, reflected. A part of it is reflected, and I is equal to I because in case of reflection the incident angle is equal to the reflected angle. Now again let's focus here. This is again refracted, this is again refracted. Since this is rarer medium, it will be, these two medium are same. This is one medium 1, this is medium 2, this is medium 1. Now this is I again, and a part of it is reflected back. Part of it is reflected back, and this angle is R, and this angle is also R. Now this angle is R, and now I can say, if I do it here like this, this angle will be I. This part is reflected and this part is, let's say, again this is refracted and this is reflected. Now let me name the points. Let's say this is A. Let's join this, and let's say this is D. This is B, and let's say this is C, and let's say this is D. Now A, B, C, D, we have all 4 points. Now let me draw a perpendicular here. Let this point be M. Let me extend this C a little bit. Okay. Now I want to find the interference pattern caused due to the two reflected waves. One that is directly being reflected. This is say ray 1. The other one, this one, ray 2. Okay, and now let the thickness be T. See, the path difference between this ray 1 and 2, that let me assume it to be del x. Let me remove this part for space. The path difference is, I can say, del x. This del x will be, let me show you, see this part carefully. here this light is moving from this much, and before it started, this light has already moved up to this, but this reflected ray actually had to travel a distance this much in the medium, then move. So what I can say is that this delta x will be the optical path inside the medium. There is AB plus BC. This is the difference. I'm trying to find the path difference, minus this length, because this was actually moved by the first path, minus of AM, mu into AB plus BC minus of AM. Now let's find what is AB plus BC. Let's see this triangle actually. This is my AB, this is my T, and this is my R. So I can say this right angle triangle, I can actually say it is T by cos R, and AB is equal to BC. Just see here, this AB, this will be equal to BC. So I can say this mu AB plus BC, AB equal to BC, so AB I can say T by cos R, and I can replace AB plus BC by 2 into T by cos R. 2 into T by cos R I can replace. Now what about AM? AM is this part. AM I can write here as this is I, this is 90 degree, this is 90 minus I, so this will be I. Sin I will be AM by AC. Sin I will be AM by AC. And also AC I can write as AD plus DC, AM plus AD plus DC, and see AD and DC are same because both are same, so this simple geometry I can write 2AD. Now from this triangle I can write AD is equal to this AD, this part AD is equal to, I can write T by, I can write here AD is equal to T into tan R. AD is T into tan R. So I can remove AD, I can replace it to T into tan R. So this is T, this is AD, and this is angle. So AD by T is equal to tan R, AD is equal to T into tan R. Now, so what I can do, I can replace AM by 2T tan R sin I. 2T tan R sin I. So I can replace AM by 2T into tan R into sin I. Tan R sin I. Now according to Snell's law, what I can write, sin I is equal to mu sin R. Sin I is equal to mu sin R. So if I replace sin I by mu sin R, and if I replace this tan R by sin R by cos R, what will I get? If I replace sin R by cos R, let me see, and so we can do one thing, we can replace this sin R into sin R. Let me write it 2TR sin square R, and I can write it 1 minus cos square R. 1 minus cos square R. And now this part I can do, this part I can write 2tr 1 minus cos square r. I can separate this part actually. 2tr by cos 2tr by cos r, minus and minus will become plus 2tr cos square r divided by cos r. Now this two term will cancel out and you can perform the simple mathematics. I am doing it like this because I have lack of space. So you can, I'm just removing one term and putting. So I am getting delta x is equal to, I'm getting delta x is the path difference is equal to 2 mu t cos r. This only you have to remember. This is important, this you have to remember. For thin film interference, for parallel case, 2 mu t is equal to cos r, that is delta x, path difference. Now let us find for the reflected waves. What is reflected waves? That means these two waves. Now see, for reflected waves, let me show you one thing. This is according to Snell's law. This is according to Snell's law. Just understand this part well. When a wave, this is a denser media, this is a rarer media. This is going from this wave is actually going from rarer to denser media. What will happen? This is going like this. In the next instant, it will go like this. Then what happens? At the juncture of denser media, it will, this wave, part of it will get transmitted and the other part will get reflected, and that will be of the opposite phase. So there is a phase reversal. So there is a phase reversal, that is a reversal of pi. So I can say for lambda we get a phase difference of 2 pi, so we will get lambda by 2. So for reflected wave, I will say del x is equal to mu t cos r minus lambda by 2. This will be there for reflected wave, because of the reflection, there is one reflection from rarer to denser. In that time there was this by minus pi by 2 that was added, that phase difference was added. So minus lambda by 2 minus pi. I hope this is clear why we take this minus lambda by 2. Okay, there are two parts. One is transmitted tr and another is reflected rf. So this reflected wave will have a phase difference of lambda minus 180 degree, or a path difference of lambda by 2 with respect to the transmitted wave. Okay, now for constructive interference, we'll get 2 mu t cos r minus lambda by 2 is equal to 2n lambda by 2, because path difference is even multiple of lambda by 2 for constructive interference or for bright fringes. So 2 mu t cos r, I can write 2n plus 1 lambda by 2. This is my condition for constructive interference. Similarly, for destructive interference, what we can get, 2 mu t cos r minus lambda by 2 is equal to 2n lambda by 2, 2n lambda by 2, 2n minus 1 lambda by 2 is odd multiple of lambda by 2. So 2 mu t cos r will be minus 1 lambda by 2, that will be only 2n lambda by 2. This is for bright fringes and this will be for dark fringes. I hope this much is clear. And these are the for reflected rays. Now let me show you what about the transmitted rays. Suppose there is the thin film, it is there, and this is medium 1, this is medium 2 with a refractive index of mu, and this is medium 1 again, and here this two parallel, and this amongst these two. Now see, Now see here, there is a reflected here, but we are interested in these two. See, this was having some phase say phi, this is also having the same phase, but in this one there is already a phase difference, path difference of lambda by 2, but here the path difference is 0. Here only refraction is happening, so same phase. This is reflected in the same medium. This is the rarer, this is the denser one, this is the rarer one, so no such thing is happening. Phase reversal, same. Now just see here one thing. Since there is no reflection, but this is the transmission from a denser medium to rarer medium, we can say that these two are having no such phase difference as lambda by 2. So therefore the same calculation will occur here. See, this is the pi by 2, this is the perpendicular distance, and this is, I can take t, and this individual will be t by cos r, because this individual is r. So I can take, and the same thing will come out to be delta x is equal to 2 mu t by cos r, 2 mu t into cos r, and there will be no additional plus or minus lambda by 2. So this is the case for transmitted. So exactly this is what I wanted to say here. And for transmitted you will find out similarly that 2 mu t cos r, that is will be equal to 2n lambda by 2 for bright, and 2 mu t cos r, that will be odd multiples of lambda by 2 for dark. This is for bright, this is for dark. So what all you have to remember, that is you have to remember that del x is equal to 2 mu t cos r, where r is the refraction angle, t is the thickness of the film, and mu is the refractive index, and that is, and for this is for transmitted. So this is what you have to remember now. And for extra I am writing in pink, there will be a plus lambda by 2 in case of reflected, case, and for transmitted case only this much is enough. Okay, now let me solve a numerical problem, then it will be very clear, the concept will be very clear. First of all, let's understand one thing. There are multiple reflections and refractions. Okay, so it is not that there is only one reflection. Okay, let me show the numerical example. A soap film of refractive index mu is equal to 1.33, and wavelength, that is lambda, 5000 Armstrong, is exposed to white light. What is white light? White light is the combination of 7 colors, or it's a band of color, not 7 colors. It's not picture, it's a band of color. Okay, we'll understand. It's a band of wavelengths. What wavelength in the visible region are reflected? The question is, what wavelength in the visible region are reflected? Okay, now see, white light, I am putting here white light. Now tell me one thing, this mu is equal to sin I by sin r, but let me tell you, this mu, this is not same for all the colors, and also some color will bend the most and some color will bend the least. Okay, I'll come to that point later, but now what we had was that delta x is equal to 2 mu t cos r, and this 2 mu t cos r plus lambda by 2 for this, plus lambda by 2 for this my reflected, it is say exposed, is reflected, what is there, that will be n lambda, that is 2n lambda by 2 for bright, let me say. So this lambda term actually comes because in case of path difference and phase difference, the wavelength matters. The wavelength matters. So in this white light, there is red, there is blue, there is yellow, there is green, there are all colors, but all of them will be having, say yellow will be like this, say red will bend the least, say blue will bend the most. They will all will be having different R, and that, and not only that, suppose I am assuming that they are all having same R, we are not going into that much details, they all will have different lambda, so their path difference will be different. So this del x, that is dependent on lambda, and white light is a mixture of lambda, mixture of wavelength. Therefore what we can, let me solve the problem, then you will understand. We have been given mu is equal to 1.33, we have been given lambda is equal to we have been given we have not been given lambda, we have been given the thickness of the film, we have been given the thickness of the soap film, that is 5000 Armstrong. That is often confused with lambda. If I have said lambda, then pardon. It is 5000 Armstrong, so 5 into 10 to the power minus 7 meter. That means this thickness. This is 5000 Armstrong. Okay, now mu is given 1.33 meter. 1.33 mu effective index, not meter. Now for reflected light, what we know, 2 mu t cos r minus lambda by 2, that is 2n lambda by 2. So we can get here 2 mu t. Now for maximum, let's assume nothing is given about r, so let's assume for maximum r is equal to 0. So for, if r is not given, take this as 0. Okay, this is the assumption. If nothing is told about r, that is the refraction angle, take I such as this r will be maximum. Okay, almost, because r is very small actually, it is almost normal incident. I think this one is clear. This is an assumption which we generally take if r is not given, or r is very small. R is given very small, we neglect it. Now this is 2n plus 1 lambda by 2. Now 2 mu t is equal to 2n plus 1 lambda by 2, I got it. Now what we can find about lambda, lambda is equal to 4 mu t by 2n plus 1. 4 mu t by 2n plus 1. Now let me formulate something here. This 4 mu t I can write here, 4 into 1.33 into say 5000 Armstrong divided by 2n plus 1. This will be equal to 26600 divided by 2n plus 1 Armstrong. 26600 into divided by 2n plus 1 Armstrong. Now let me see for different values of n what it is coming. White light, I repeat, white light is a mixture of lights having different frequencies, or rather it's a electromagnetic spectrum. Beyond white light also something else is coming. It is exposed to, actually not white light, I should say it is exposed to sunlight. That means it is having all possible spectrum, some extending beyond the visible range as well. Now n is equal to, let's say 0. If n is equal to 0, my lambda 0, let me say, that I am getting 26600 divided by 1, that is 26600 Armstrong. This is in the, I can say, IR range, infrared range. You all know the range of visible spectrum, it is 4000 to 8000 Armstrong. Now What is lambda 1? It is, let's say n is equal to 1. 26600 divided by 2 plus 1, that is 26000 divided by 3, 8667 Armstrong. This 2 belongs to IR. Now the next one, what I can write here, lambda 2, n is equal to 2, 26600 divided by 2 into 2 plus 1 divided by 5. So I can say this is 5230 Armstrong. This is actually belonging to visible region, VIS. Now this is visible region, and the last one, let me see, this one see, let me see now, n is equal to 3, 26600 divided by 2 into 3 plus 1, that is coming out to be 3800 Armstrong almost, and this 3800 Armstrong is less than 4000, so it goes to ultraviolet, that is UV. So I have only one such wavelength which is actually belonging to the visible region. So I think you have now understood that only one ray will be reflected in the visible region, one band of wavelength, that is lambda for n is equal to 2. That means in the second fringe we will be getting the visible wavelength. So that's all for today's video, and if you like my video then please subscribe to my channel and click on the bell icon. Thank you.